So question 2.5 is the last question of this section 2 of the Qiskit advocate exam. And the question says, how many gates are in the quantum circuit that results from transpiling the following quantum circuit using only the pass LookAhead swap? Assume the following coupling map, and we're giving a list of numbers here. So there's a lot of terminology here. So you can see here transpiling, pass, LookAhead swap, and coupling map. So in order for us to fully understand this question, we need to go over what the process of transpiling is. So let's take a look at that. So question 2.5. And let's start by defining what is transpiling. So transpiling is the process of converting a quantum circuit into an optimal, and I put optimal here in quotes because sometimes we just want to be able to run a circuit, not necessarily optimize it. So it's the process of converting a quantum circuit into an optimal version that can run in a specific hardware. And by hardware we mean quantum processing unit, or QPU. So this process of transpiling consists of many different steps, and I'm not gonna list them all, but let's go over some of the most critical ones. So for example, when you're trying to optimize a circuit, one of the things you might want to do is consolidate gates. So consolidate gates, and what I mean by this is, if you, for example, have a circuit where in some part of it you have, for some reason or another, two Hadamard gates just back to back from each other. Well, we know that since they're in Hermitian, they're equal to having the two of them is just equal to having the an identity matrix, right? So they kind of, let's say they cancel each other to some extent. So this is just like not having anything. So in the transpiling process, the algorithm will go through different gates and try to unify them into simpler gates. The process will also consist of replacing gates, some gates, like in this case a Hadamard gate, with what are known as basis gates. So basis gates are the gates that are inherently available in a quantum processor, and they have been calibrated. So for example, they could be a specific piece of hardware that only supports in terms of single qubit gates, only supports rotations about the z-axis and the x-axis. So if you have, for example, a Hadamard gate, the way this will run in hardware is there's no specific way to implement directly the Hadamard, but there's an equivalency with the basis gates, and it will consist of first running an RZ gate by pi over 2 rotation, followed by an RX gate with also a pi over 2 rotation, and then followed by another RZ gate with another pi over 2 rotation, and we could verify that this rotations, and if you look at it, for example, in terms of the block sphere, you would see that if you perform those rotations in that order, you would get the same equivalent transformation as a Hallamar gate. So that's part of what a transpiler would do, would be to map some general gates like the Hallamar gate to specific gates that are part of the hardware. Another part of the process is mapping virtual qubits, let me write that again, virtual qubits to the actual physical qubits. And what we mean by this is, let's say for example you want to run a 2-qubit circuit, right? So let's say you have a 2-qubit circuit that is just, let's say, a CNOT gate. So it's a CNOT, and you have that CNOT between qubit 0 and qubit 1, right? So and now let's say that you're going to run this in a quantum processor that has, let's say, 4 qubits. So as you know, in hardware, specifically when we're talking about superconducting qubits, these are implemented on a piece of silicon, right? So in a chip, and the qubits are physically placed somewhere in that chip. So let's draw them as little squares here, and those qubits are connected to each other, but they're not all interconnected to each other. But maybe let's call this qubit 1, qubit 2, qubit 3, and qubit 4. And maybe the way they're connected is, qubit 1 and qubit 2 are connected, so you can apply 2 qubit gates between the two of them. Qubit 2 and qubit 3 are connected, and 3 and 4 are connected, but 1 and 4 are not connected, for example, or 1 and 3 are not connected, right? So when you have this circuit that you have generated, well, there are many ways in which you could actually map the circuit into the actual hardware. If we, for example, now draw 4 lines that correspond to each of those 4 available qubits that we have on hardware, well, since all of your circuit is just a 2-qubit gate, you can map it into any of those 4. So let's say for some reason the fidelity or the level of performance of your CNOT gate from qubit 1 to qubit 2 is not as good as the level of fidelity between 2 and 3, then what you want to do is actually implement that CNOT gate between qubits 2 and 3. So then the way you would implement this circuit in the actual hardware will be something like this. And then here what you're doing is you're mapping qubit 0, we call this virtual qubit, your virtual qubit 0 to your actual hardware qubit 2, and your virtual qubit 1, you map it to qubit 3. And here I'm labeling 1 through 4, but if you want to follow same convention as it's following Qiskit, you start labeling again 0, 1, 2, 3, and then what we're actually doing is mapping from qubit 0 to qubit 1 and qubit 1 to actual physical qubit 2. That will be also part of the transpiling process. You can either specify manually to the transpiler that this is what you want to do. You want your qubits 0 and 1 to map to the physical qubits 1 and 2. And then we can write physical qubit 0 and physical qubit 3 here. Or there could be some sort of more advanced algorithm that will find which is the connection with the best fidelity and try to find a way to map your circuit into those specific qubits so you get the best performance. Another one that is very important is the transpiler would it would add some additional gates that would allow to guarantee the circuit that we have specified can run in hardware. And what I mean by this is, let's say now we have the same piece of hardware, right? And I'm gonna simplify it here, and I'm just gonna draw them as little circles here. So this is, we call this qubit, physical qubit 0 connected to physical qubit 1 connected to physical qubit 2 and physical qubit 3. And let's say that what we would like to do is implement, let's say this is part of a much larger circuit, but in this circuit we have a CNOT gate, let's say between qubit 0 and qubit 3, right? So as we can see here, well, there's no direct connection between qubit 0 and qubit 3, so there's no way to implement this in hardware, right? And as we saw before, well, we could maybe move this qubit 0 and map it to the physical qubit 2 so that we can implement the CNOT between those two. But let's say that this is part of a much larger circuit that is using all 4 qubits, and we really need to make this connection, this CNOT connection between 0 and 3. So the way we would do this is by introducing swap gates. So what we would do is, let's copy this down here, and what we would do is, instead of trying to make that CNOT connection there, we would add a swap gate between qubit 0 and qubit 1, then another swap gate between qubit 1 and qubit 2, and then apply the CNOT between qubit 2 and qubit 3. So that way, what we would see here is that since the swap gate basically swaps these 2 qubits, then it's the same as now having qubit 0 here, and then you apply another swap gate here. It's like having qubit 0 here now. So then you can directly apply that CNOT between the 2 qubits that you're interested in. So this is what it's usually referred to as routing, and this is precisely what we're being asked in this question is, well, how does the final circuit look like if we use what is known as the LookAhead swap routing? And what LookAhead swap is basically an algorithm that maps our circuit into the QPU, but tries to minimize the number of swap gates by following some series of steps. And you can go to the Qiskit documentation for the LookAhead swap, and here you can see what the steps that are followed are for this specific algorithm. And then for this question, what we need to do is go ahead and code this and see how many gates we end up with at the end. So let's go ahead and do this in Qiskit. So let's do as usual, from Qiskit import quantum circuit, and let's go ahead and implement the circuit. So we have QC quantum circuit, and we have 5 qubits in this case, and we're going to apply a Hadamard gate on qubit 3, then a CNOT gate between qubit 0 and qubit 4, another CNOT gate between 3 and 0, and another CNOT gate between 2 and 4. And then let's go ahead and draw that, and let's make sure it looks just like what we have here, and that seems correct. So what we're going to do next is we're going to import from Qiskit transpiler, import coupling map, and I'll explain this in a second. And then we're going to import also the pass manager. And from Qiskit transpiler passes, import LookAhead swap. So just in terms of terminology, the coupling map is basically a series of numbers that tells the transpiler which connections between qubits are allowed. So as we saw before in this example, we had qubit 0 is connected to qubit 1, qubit 1 is connected to qubit 2, and qubit 2 is connected to qubit 3. So our coupling map would be a series of numbers, of pair of numbers that would look like 0, 1. That means that 0 and 1 are connected. Then another pair of numbers, 1, 2. And then another pair, 2, 3. And that specifies the connection between qubits. If we had a different layout, something, I don't know, something like this, where, this is 0, 1, 2, and 3, then the series of numbers will be, 0, 1. Now 1 and 3 are connected, and 3 and 2 are connected, but not 1 and 2. So this is basically the coupling map. And then this other term, pass manager, is basically is a piece of software that is responsible for ordering and scheduling what are known as passes. And passes, transpiler passes, are just the circuit transformations we just discussed. So, for example, reducing the number of gates by consolidating them, or specifying where to match each qubit into the physical hardware, and so on and so forth. So that's what is known as a transpiler pass. It's just a circuit conversion. And the pass manager, what it does is it's responsible for ordering and scheduling each of these passes during the transpiling process. Okay, so let's import this three things, and let's go ahead now and specify our coupling map. So let's call this C map equal to coupling map, and we pass this in the form of a list. So let's do coupling list, which is one of the parameters, and we're gonna give the series of numbers that we were given up here. So let's just actually copy and paste this. So let's copy this, which is 0, 1, 1, 2, 2, 3, 3, 4. Let's just paste that here. And then now let's specify our LookAhead swap algorithm, and we have to specify the coupling map here, and we're gonna just pass C map, which is the one we just defined. Then we're gonna define the pass manager, which only consists of this LookAhead swap step, and then we're gonna transpile our circuit by doing this. Let's define this in a separate variable. Let's call it QC trans for transpile circuit, and we just do pass manager, and then we run this on the quantum circuit we specified up here. And now let's go ahead and draw that circuit and see how it looks like. And here we can see that we have introduced some swap gates in order to make sure that we can apply the CNOT gate between qubit 0 and qubit 4, which are not physically connected, as you can see here in the coupling map, right? 0 is connected to 1, 1, 2, 3 to 4, but 0 is not connected to 4. So we introduce some swap gates to allow for this CNOT gate to be applied. Same here, from 3 to 0 and from 2 to 4. And the LookAhead swap does this in an efficient way that minimizes the number of swap gates introduced. And then in order to find out what we're being asked for, which is, how many gates result at the end of this process, we do qctrans.size, and we get that we have a total number of 8, which is exactly what we have here. So the answer to this question is 2, which is equal to 8 gates.